Hey guys, wanted to get you those last couple free response questions. So in case you wanted some extra practice, take a look at that. All right, so I'm going to walk you through those last two that we didn't get to yesterday. Okay. All right, so if we look at these questions, these next two fall into the real short free response category. All right, so it says at 30 degrees, the reaction is thermodynamically favorable, which means it should happen. All right, but no reaction is observed to occur. However, at 120, the reaction occurs at an observable rate, meaning it does happen. And the question says, explain how the higher temperature affects the collisions between the reactant molecules so that the reaction occurs at 120 degrees. All right, so this ties into all of the stuff that we were talking about with catalysts, all right, and reaction mechanisms, and this idea of activation energy. There's this minimum threshold of energy that you have to overcome to have the reaction occur. Right? So why is it that a higher temperature is leading to a more observable reaction? Remember, higher temp means molecules are moving faster. If they're moving faster, they have more energy. They're colliding with more force. That means more molecules have the average kinetic energy needed to get over the activation energy barrier. All right, so the increased temperature gives more molecules enough energy to overcome the activation barrier, which is what you would want to say for letter I. Into the II, it says the graph below shows a distribution for the collision energies of the reactant molecules at 120. Draw a second curve that shows the distribution of it at 30. All right, so this is one of those Maxwell-Boltzmann type problems. Right? There's a couple things about those that could happen. The curve they're showing you looks like this. And it's got your activation energy on it. That's the one in the question. All right, so if I insert a catalyst, I slide the activation energy barrier back, right? I lower the activation energy, more of the curve is past it. So the number of molecules that have that criteria of being past the barrier increases. That's why things speed up. Right? If I increase temp, I shift the curve to the right and down. And if I shift the curve to the right and down, more of the curve gets past the line. Right? But this is saying the curve is at 120. They want to know, what does the curve look like, right, at 30, right? They're asking the reverse. Right? So if we cool things off, what happens is the curve shifts to the left and gets taller, and make sure that you zero it out before the activation energy barrier, because we know at 30 we don't see any of the reaction occurring. All right, so you got to shift it left and make it taller, and the curve needs to finish before the barrier when you would sketch that, because we know it's not happening. All right, so that's what's going on with this thing here. That was a Maxwell-Boltzmann type problem related to catalysts. This guy here, another short free response. It says, we do a study, all right, of the decomp of a reaction. They collect the data. So you're looking at time in one column, concentration in the other. All right, so if we have time in one column and concentration in the other, all right, what's happening is we can do our integrated rate law checks. All right, and if we're going to do our integrated rate law checks, and give me like 5 minutes, okay? We do our integrated rate law checks, right? We would do concentration versus time. The graph we're looking at is our check for zero order. It's not linear. Right? They didn't give us the other two checks, the ln versus time or the 1 over versus time. So the student's proposing that the rate law is rate is k, right, times CONH2, all right, to the first. So it's saying it's first order. And it wants us to say, how is the data supporting that rate law? So you're going to say, well, the picture isn't matching the correct thing. Well, remember, whenever you have concentration versus time, there's that sneaky check for half-life. So if you look up into this picture, you can see how long a half-life is. We started at time 0 at 0.10. Right, if we're at 0.10, when we drop to 0.05 rather, we know one half-life has occurred. So to go from 0.10 to 0.05, it took us 10 hours. So if 10 more hours goes by and it cuts it in half again, we know we have a constant half-life, which confirms a first-order reaction. So sure enough, 0.05 cuts to 0.025. That happens at 20 hours, right? So it's the same interval. 10 more hours, cut it in half again. So in example 1, E, letter I know that it confirms the rate law because we have a constant half-life based on what we see in the graph up above. II says using the proposed rate law and the results, determine the value of the rate constant K. Include units in your answer. So you could do one of two methods. You could do the integrated rate law because you have the 0 point. And that would be one method. Right? We know for first order, it's the ln of A at some time equals ln of AO minus KT. Right? And we have everything we need. We have our 0 point, right? Because we have time 0 hours, it's 0.100. So you could have ln 0.100 minus, we're looking for K, and then all you do is you pick a time with its concentration there. Right? So we could pick 30, and the 30 would be the 0.0125. So then it would be ln 0.0125. All right, so that would be one way to do this. All right, and then we just isolate what we're looking for. Right, so if we did that, the ln of 0.0125, right, that is negative 4.38 equals the ln of 0.100. That's negative 2.30 minus K times the 30. All right, so you solve that guy for K, and you're going to get negative 4.38 plus the 2.30 divided by negative 30. Right, and if we do that, we're going to get a value of 0.069, right? And then our units, right, if it's first order overall, it's m, 1 behind an opposite, that's to the 0, time negative 1, which will be hours negative 1. There's method 1. That works if you have the 0 point. Method 2, which works no matter what, is you find the slope of the line. Just be careful. The numbers you're looking at in the table are not your first order checks. That is your 0 order check. So if I wanted to get K, right, I would do y2 minus y1 over x2 minus x1. The x's are easy, right? You pick the time. Right? T final 30 minus T initial. Then the y2 and the y1, you have to realize I have to take the ln's of those. So I'm going to take the ln, right, of the 0.0125 right, minus the ln of 0.100. And sure enough, you're seeing the same math setup. Right? And if you see that same math setup, inevitably, you're going to get the same outcome. All right, so that's what you would do there for II. Either method would work fine. And then last but not least, it says the student learns the decomp was run in a solution with a pH of 13. Describe an experiment including the initial conditions that you could change and the data you would gather to determine whether it depends on the concentration of OH negative. All right, so what would we initially monitor and then change? I would say that we would monitor maybe the absorbance, right, of the OH negative over time, right, as we initiated the reaction to see if we could generate a graph like you see above. All right, so one more of those still to come later. All right, but this one will get you guys going.